Section 10.4, Adding, Subtracting, and Multiplying Radical Expressions. Selected homework problems. Number 1. The square root of 50 minus the square root of 98. Here we're being asked to subtract two radical expressions. Now, to subtract or add radical expressions, you have to have like radicals. And we do not here. So first we simplify. Simplify the 50 by factoring it such that one of the factors is a perfect square. 25 times 2. 25 is our perfect square. And similarly, factor 98 by writing it as 49 times 2, where 49 is a perfect square. So as you can see now, we have factors of 2 under both radical signs. That's going to become our like radical. That's what we're aiming for. So on the third line, we use the product rule, putting each radicand, each factor of the radicand under a separate radical sign. Square root of 25 times the square root of 2 minus the square root of 49 times the square root of 2. Now, the square root of 25 can be square rooted because 25 is a perfect square. 5 squared is 25. So the square root of 25 is 5. And similarly, the square root of 49 is 7. So now you see we have like radicals in both terms. The root's the same and the radicand's the same. That's what makes them like radicals. So just like we would subtract the number coefficients when we have like terms here, we subtract the coefficients on the radicals, the 5 and the 7. 5 minus 7 is minus 2. So we have minus 2 times the square root of 2. And that's our answer. Number 2. 5 times the square root of 3 times x cubed plus 3 times x times the square root of 27x. Again, our radicals are square roots, but here in this problem we're adding and we have variables as radicands, as parts of our radicands. So first thing, again, we want to make like radicals. To do this, we're looking for perfect squares. Now in the first term, 3 is not a perfect square, but we can factor x cubed, just like we factored 25 and 49 on the previous slide. We can factor x cubed such that one of the factors is a perfect square. And we do this by rewriting x cubed as x squared times x. And you see there in the blue is your perfect square. Similarly with the second term, I rewrite 27 as 9 times 3, where 9 is the perfect square. Then on the third line, we use the product rule to write the perfect square radicands under separate radical signs. So I took out all the blue and put them under separate radical signs. So we have 5 times x squared, the square root of x squared, 5 times the square root of x squared, where x squared is a perfect square, times the square root of 3x plus 3x times the square root of 9, where 9 is a perfect square, times the square root of 3x. So now you also see on the same line that the square root of 3x is on both terms now. So we're forming our like radicand, our like radicals with the same radicand and the same root. so that we can then add our two terms. So on the fourth line, we square root the perfect squares. We have 5 times x, square root of x squared is x, times the square root of 3x, plus 3x times 3, which is the square root of the 9, times the square root of 3x. Simplifying the 3x times the 3 on the second term, we get 9x. So now we have 5x times the square root of 3x plus 9x times the square root of 3x. So we have 5x square roots of 3x's plus 9x square roots of 3x's. So altogether we have 14x square root of 3x, and that's our answer. Number 6, the cube root of 9 over 27 minus the cube root of 9 over 4. Well, now I have, instead of square root, cube root, so I'm looking for perfect cubes in order to simplify the radicals in both terms. 9 is not a perfect cube, but I know that 27 is, because 3 times 3 times 3 is 27. So using the product rule, I separate the two radicands in the first term under separate radical signs. That's using the quotient rule. Using the quotient rule, I separate them. And I get the cube root of 9 over the cube root of, and I rewrite 27 as 3 cubed. The second term, cube root of 9 over 4, stays the same. But now on the third line, the cube root of 3 cubed is 3. So the root and the power, again, cancel out the cube root. The power cancels out that cube root because those are opposite operations. So we get the cube root of 3 cubed is 3. So now we have two like radicals in our numerators, but one of the fractions has a denominator of 3 and the other of 4. So these are not like fractions. And when we combine radicals or fractions, we need like radicals and like fractions. So first we need to get a lowest common denominator. And the lowest common denominator is between 3 and 4. The lowest common denominator of those two numbers is 12. So to make 3 12, we multiply the first fraction by 4 over 4. To make 4 12, we multiply the first fraction by 3 over 3. And we get 4 times the cube root of 9 over 12 minus 3 times the cube root of 9 over 12. So now we have like fractions. We have 4 cube roots of 9 minus 3 cube roots of 9. So actually 4 twelfths cube roots of 9 minus 3 twelfths cube roots of 9. But we're going to just subtract the numerators. 4 minus 3 is 1. So that leaves us with 1 cube root of 9. So we have 1 cube root of 9 in the numerator over 12. And that's our answer. Number 15. Multiply the square root of 7 plus x all squared. This means that our base is square root of 7 plus x. So to translate that, we write the square root of 7 plus x times the square root of 7 plus x. And then we FOIL. The square root of 7 times the square root of 7. By the product rule, that's the square root of 7 times 7, which is 49. Square root of 7 times x is, I write it as x times the square root of 7. And then the second term times the first is again x times the square root of 7. And then x times the x is x squared. Now, 49 is a perfect square, so we squared our square root by going square root 7 times square root 7. And the square root of 49 is 7. X times the square root of 7 plus x times the square root of 7 is altogether 2x times the square root of 7 plus x squared. And then I just rewrite this polynomial with the x squared term first. It's not incorrect to not write it first. It's just more standard. So I write x squared, highest power first, followed by plus 2x, which is the next highest power on the variable, plus 2x times square root 7, plus 7. And that's our answer.